talking about this. You know, what are leading infectious diseases that cause death? How do they get into the body? Well, a lot of them, accounting for 13 million deaths every year, are entering through the mucosal routes. Okay, so all of those big red balloons that I added to this nice graph from NIH, those are the ones that that are mucosally acquired infections. So this is a major problem, and we really need to understand what's going on there. All right, so there's some challenges. Number one, you've got lots of things going on. This is a very active site. Lots of trafficking because, are all of your lymphoid organs at the mucosal surfaces? Not really, but that's where the pathogens are coming in. So how do we now connect all of these pieces so that we can make an effective immune response? All right, so when we're talking about mucosal tissue, we're talking about some different areas. So the gut-associated lymphoid tissue are GALT, the bronchus or BALT, the nasal-associated are NALT, and then the genitourinary mucosa, which we'll touch on for just a second. Something we won't touch on, but which is classified as a mucosal surface for lots of physiological reasons, are mammary glands. All right, so what are some of the very specialized features of the mucosal tissue? So first, it's an epithelial structure, right? And we'll talk in a little bit more in detail about some of those specialized traits of epithelial cells in the second hour. But the epithelial cells at all of these different surfaces are going to be very highly specialized for that specific function and for that specific location. Things that we need at that barrier surface in the lung versus in the gut are going to be very different, and so those cells are specialized as that first line of defense. All of these epithelial barriers do have some specialized lymphoid structures, different at each, to some extent, at each mucosal surface, and they're located just under that epithelial barrier, but very tightly geographically associated, not chemically, physically associated. And they're very organized structures, but they're not technically a lymph node. They're not encapsulated like lymph nodes and the spleens are, but you're going to see, if you look here, and I didn't switch the pointer, but if you look down here at the bottom, okay, interest of time, down here at the bottom, this very well organized structure, that's one of the lymphoid follicles, as we call them, that are associated there under that epithelial surface. And what we'll see in a minute, that's the gut mucosa, all those ciliated, not ciliated, that's lung, sorry, the microvilli in your GI tract. Excuse me, that's what you see there. All right, and you have all sorts of immune cells, both adaptive and innate, in those structures. And then the function of those surfaces are making that immediate immune response at some level, primarily on an innate level, through the innate lymphoid cells that are there, the ILCs, and then also educating the dendritic cells, activating those that will then traffic and call in, recruit the adaptive T cells and then activate the B cells. But the other important fact is homing, because as those dendritic cells are activated in those follicles, they're imprinted with a signal that says, I came from the gut mucosa. And not just the gut mucosa, whether it's the small intestine, the large intestine, but very specific regions. And that signal serves as a homing signal when the dendritic cell activates the T cell for it to go back to that specific region. All right, and we'll talk about that a little bit more in a few minutes. All right, so what are some of the challenges specifically for the gut mucosa? Number one is, how do we know this much? We're going to spend most of this hour or this lecture period talking about the gut mucosa. Why do we know that? Because you can take the intestinal tract, open it up, pull out the intestines, open up that tube, and then peel off that epithelial layer. And so you've got a really easy way to isolate all the cells, isolate the surface, and then study it in whatever way you want. Harder to do in the lung, can't do it on other mucosal surfaces, so that's why we've got so much information on the gut mucosa and relatively less on the other surfaces. So what is it about the GI tract? Number one, it's very large, 200 square meters, the size of a tennis court. If you completely stretched out your gut mucosa, and that's basically just stomach and intestinal tract, it would cover a tennis court, right? But each of those segments are phenotypically and functionally different, not just from the GI absorptive digestive end, but also from the immunological end. And the other major job is discriminating. All right, we all know we've got lots of bacteria in our lower GI tract and the upper, but those are there for a purpose. Part of it's digestive, other things. But how does the immune system, this epithelial barrier, differentiate the cells that belong, our normal flora, the good cells, versus those pathogens, the E. coli that you ate when you had that salad on a mission trip, or the C. diff, Montezuma's revenge, right? Or if you're on the cruise ship and you eat something you're not supposed to. It's not that you're breathing because you've got your mask on, but you eat that other food that you shouldn't, that shellfish or that salad, those raw vegetables, and get norovirus. Once you get to your virology, hopefully you'll talk about that. Before SARS, that was the most heavily associated with cruise ships. Well, that may change now. But anyway, how does your immune system, how does your GI tract differentiate between those and know, hey, I'm going to ignore this nice normal E. coli, but I'm going to make a response to that enterotoxigenic E. coli that gives us the Montezuma's revenge, or to that norovirus. Okay? And then, just food. Are we made of oatmeal? Who had oatmeal for breakfast? Are we made of oatmeal? No. Are we made of tuna? Dinner last night? No. So how does the GI system and the immune response of the GI system know that I'm not going to make a response to that foreign substance? Because it's safe, it's food, it's what nourishes us, but it is foreign. So why do we not make an inflammatory response to it? All right? So the solution is that you've got this very highly organized and specialized structure. All right, so what are some of those specialized structures? First, the epithelial layer itself. So it arises from stem cells, so epithelial stem cells. They're here at the very base of that epithelial layer. So there's a very thin layer of undifferentiated stem cells that then, when they get the signals, they differentiate and form that epithelial barrier. In the gut mucosa, it's one cell thick, right? Then you've got your absorptive epithelial cells to do the job of absorbing all the nutrients. You've got goblet cells. And goblet cells secrete mucus because we need all of that mucus layer in the GI tract to protect, think that in the stomach, protecting against the acid that is made, other digestive enzymes, and other insults. You've got the microfold or M cells, which are basically just an elevator for substances to get from the lumen of the GI tract into the sub-epithelial layer. So it's a way of easy passage. M, microfold, and they just engulf, fold in those foreign particles, and then they transcytose, pass through that cell, untouched, they're not phagocytized, and then are delivered to the submucosal barrier, or submucosal layer of the epithelial barrier. And then you have Paneth cells, and typically these are located, since I've been over here, these are located at the very bottom of this villus crypt, and those are cells that secrete a lot of these antimicrobial peptides that then exist in the environment and help protect against invading cells. All right? Specialized molecules are the poly-Ig receptor, the mucins, and the defensins. We'll talk about poly-Ig and mucin in a second. Defensins are some of those antimicrobial peptides. Alpha and beta are the two most, but there's a larger family. And so they, name implies, defend against, so they're enzymes and have other antimicrobial properties that then can attack invading bacteria or other organisms that are deemed to be not belonging or troublesome. Right? So what about mucins and goblet cells? So if you look at this bright pink or dark pink staining, that burgundy, that is a special histological stain that stains glycoproteins, okay? Where you can use it in mucosal surfaces really well, is it stains mucus, because mucins are just really complex polysaccharides. Okay, so you can see, and again, here are all the microvilli that form that epithelial barrier in the GI tract, and you can see all of the mucus-producing cells, those goblet cells, that are lining each of those microvilli. And their only job as a goblet cell is to sit there and be a factory and pump out all of those mucins that then form that mucus barrier. Okay? What is the purpose of the mucus barrier? So it buffers, again, we talked about protecting against the acid, but then it also helps buffer the microbes from the epithelial cells. So it's just kind of that transparent barrier, that sheer curtain that says, okay, I'm going to limit as much as I can the direct contact that these bacteria have with the epithelial cells, and then any, as we'll see in a minute, any of the immune cells that are interdigitated, slipped in between those epithelial cell barriers. All right. Other name that you might hear the mucus barrier called, because you have the mucus produced, and there are some proteins that are produced that can then form a complex. That complex is called the glycocalyx. Don't hear it very often, but you may encounter it in a more physiological term versus the more general immunological term. All right. So there are different mucins, different types, different levels, and different glycosylation patterns. And this is one way that we can tell, especially in cancers, whether something is healthy or not. Okay. Because that, the mucins, for whatever reason, are very often mutated in some cancers, and not just GI cancers. And then, in those different layers, you have different mucins produced. Oops. Okay. So Paneth cells, remember, they're there at the bottom of that crypt. They're secreting the antimicrobial peptides, including alpha and beta defensins. The alpha defensins tend to be in the non-absorptive cells, where the beta defensins are being secreted by the absorptive epithelial cells. All right. And then the other immune cells can also produce the alpha defensins, especially neutrophils. All right. Doesn't that make sense? What is them? As we'll see in a couple weeks, one of the main jobs of neutrophils are phagocytosing all those bacteria, right? So lots of bacteria in the gut. So let's connect those two dots and have the neutrophils make those alpha defensins. Okay. How do the defensins work? They can be directly cytotoxic to the pathogens, so they kill once the bacteria bind those defensins. A program is induced in those bacteria in which they die, but then those defensins can also activate the local immune cells. So you've got an indirect method of killing through activation of those cells. Okay? Defensin production can change with disease levels, so this can give us a way to monitor the GI secretions and help diagnose the patient. Okay? Part of that's due to the different immune signals that are received by those GI epithelial cells. And there are specific linkages to autoimmune diseases such as Crohn's disease with mutations in those defensins. Okay? So again, that dysregulation of an immune system that then results in disease. Okay, so microfold cells. All right, remember, these are the cells that kind of engulf the particle and allow it to transcytose. So here is a nice cartoon that shows that. So here's the lumen up here. So here's your absorptive cells, your M cell. Here is the lumen and the bacteria that is detected and then is endocytosed and passes through that M cell untouched and is delivered to, under the M cell, you have a lot of these lymphoid structures that we talked about. There was the diagram of in one of the earlier slides. And you can sort of see that here, okay? So that is one of those lymphoid structures. And so the gold star that I put up there at the top and that little black dot, that's a bacterium that is being engulfed. So you can see how there's kind of that dip that has started to occur. That's where the microfold cell has been triggered and it's going to start engulfing that bacterium to allow it to pass through and be delivered to that microfold cell. Okay? there is no degradation, there's no processing, nothing happens to that, whatever it is, whether it's a particle, whether it's a bacteria, nothing happens to that particle, that bacterium, as it goes through the cell. It's just free passage. Okay? That can be really good for absorbing or transporting different biochemical molecules. It can be good because since you're delivering it to an area that is rich in dendritic cells for detecting and defeating pathogens, problem is there are several bacteria that usurp this pathway that can establish an intracellular infection in these macrophages, less in dendritic cells, but in the macrophages that are also in these lymphoid follicles, and then establish an infection. Okay? You'll talk about those in micro, well, you already have because you talked about bacteria. So, like Listeria, they've got specific enzymes that, facilitate this process. So that's the mechanism that we have that the bacteria can now use to their own advantage. Okay? If we want to talk about viruses, poliovirus specifically has a receptor that binds on M cells. And so this is the way, how do we get infected with polio? Is drinking that contaminated water, typically. Okay? I know you have a virology. So you drink that contaminated water, but now how does the virus get from the lumen of the intestinal tract to the muscle where it causes the disease, right? Its first pathway is binding to the M cell, transcytosing, and then binding specifically to cells in those lymphoid patches, the pyre patches. Okay. So the epithelium kind of makes sense. Got to detect all these pathogens, so they express a lot of PRR, so the pattern recognition receptors. Toll-like receptors, lectins, C-type lectins, and there's a limited number, and so this is one way in which the body can discriminate between what we don't want to make a response to as far as the commensal bacteria or to food particles or whatever versus making the response to the pathogens. Okay. On the apical surface, so the cells, the side of the cell that faces into the lumen, there's a very limited number of the PRRs. Some of them are there, but a much lower level than what is found on the basolateral surface. Okay? We just talked about how some pathogens can, through the microfold cells, get from the lumen into the basolateral side, that subepithelial layer, and so kind of makes sense that if you want a higher level of expression there to detect those invaders, right? Versus making an inappropriate response to all of the bacteria, the huge numbers that are on the apical surface. So that's mechanism number one. And then there's the threshold of activation. So the PRRs on a macrophage, on a dendritic cell, on other cells, have a lower threshold of activation. So the level of signal that's generated for that dendritic cell to now become active is lower than it is for these barrier epithelial cells. So you have a higher signal level that must be met if you're an epithelial cell on that PRR binding before you become activated, before you start secreting your cytokines, before you start sending out the signals to now recruit other innate cells. Okay? All right, so lots of antigen presenting cells in all of these barrier surfaces. And we've got some specialized names for some of the dendritic cells at these surfaces. The liver is part of the GI tract, and in the liver, those specialized dendritic cells and macrophages are called Kupffer cells. In the GI tract, we don't have a special name for them, but as far as the intestinal part, and that's what most of our conversation is going to be on. Okay, but these cells, a lot of them are in this the subdermal layer, but you also have some that, as you can see in this image, that have some of those dendrites interdigitated in between those epithelial cell layers and actually extending through the epithelial layer into the lumen of the gut. And they're just sitting there, sampling, tasting all of those different microbes that are going through to say, all right, Yeah, you get a pass, uh-oh, red flag goes off. There's problems. We need to start thinking about a response here, right? And then those dendritic cells are educated to be tolerant to the commensal flora, but then also to react to the pathogens because of those thresholds of activity that we were talking about, okay? Important point is that when those dendritic cells are activated, they then leave the gut. They may, a few of them that are residing there in those lymphoid follicles, which can't believe I don't have a slide of that, but those lymphoid follicles in the gut are called Peyer's patches, P-E-Y-E-R-S. Okay, so that's a special name for that structure there under the M cell. And so some of the dendritic cells will traffic to that Peyer's patch and educate. There's a limited number of naive T and B cells there. But most of the activated dendritic cells and macrophages, activated APCs, are going to leave the gut lumen, enter the circulation, whether it's the lymphatic or the venous circulation, and then go to a more distant, actual formal lymphoid organ, the mesenteric lymph nodes, other lymph nodes, to the spleen, and activate the greater number of T cells and B cells there. Okay. Those T cells then have to traffic from that secondary lymphoid organ back to the gut lumen, specifically where the infection is occurring, right? How does this occur? This is the homing I referred to a minute ago. This process in the gut is regulated by vitamin A. Okay. That dendritic cell, before it's activated, synthesizes retinoic acid, okay? It absorbs vitamin A that we eat in our diet, if you're eating lots of carrots and other leafy greens, and then that vitamin A is converted to retinoic acid once that dendritic cell becomes activated, okay? You don't have to know the dehydrogenase or the chemical structure of that particle, okay? But it's converted to, the vitamin A converted to retinoic acid. When that dendritic cell gets to the lymph node, to the spleen, where it's activating the T cells or the B cells, it releases that retinoic acid as it's activating that T cell. Okay? That retinoic acid causes the expression of very specific integrins on that newly activated T cell, and imprints on it a signal that says, use this integrin. And remember, integrins are some of the trafficking molecules. They bind to those epithelial and endothelial ligands that allow them to transmigrate, to diapedese through those endothelial and epithelial barriers, and then traffic to the specific location, okay? And then, based on that integrin expression, the T cell then homes to the specific place in the gut because of that RNA, that retinoic acid signal that has been imprinted on it. Does that process make sense? A little bit? Okay. That's homing. And so that's why, think about it. Remember, size of a tennis court. How does the T cell want to find the right place where you've got that E. coli infection or that norovirus infection? So the integrin is the cell adhesion molecule that allows trafficking. So it binds to specific ligands. So one of the integrins that we talked a lot about in the T cell is LFA, that binds to the ICAM on the endothelial cell surface. So this integrin that was listed on the last slide, I'm not going to say the name because you don't need to know that, just know it's a specific integrin, binds to ligands on the epithelial and endothelial barriers to allow it to pass through those barriers, and then so it's got to leave the lymph node, enter the circulation, go to wherever it needs to go in the GI tract, leave the circulation, and then maybe cross that epithelial cell barrier on the gut to get to the site where you've got that E. coli infection. Okay, so the integrin is the binding partner that allows all of that passage. It pays the toll at the toll gate. Did you all hear the question or figure out what the question was? Sorry, I didn't repeat it that time. So, what was the job of integrin was the question. All right. So, the neonatal FC receptor. So if you look at these structures, you can see that it looks a lot because here's the, where is it? Here's the FC N receptor. Looks a lot like MHC, right? It's even got beta-2 microglobulin, like MHC class 1 has, but it's not. It is a molecule that is expressed both in neonates, as the name suggests, but it's also expressed in adults. So in neonates, it's highly expressed on the gut epithelium. And why is that? Because the function in a neonate is to absorb all of those maternal antibodies that are being delivered to the baby, especially, well, not especially, when mom is breastfeeding, okay? And so all of that breast milk is really rich in antibodies that mom has made. The baby drinks that. It's bound by the FC. The antibodies are bound by those maternal antibodies by the FcRn receptor, and then transcytosed across the epithelial barrier and delivered to the circulation of the baby. Okay, that's part of maternal immunity. All right. The FcRn receptor is also expressed throughout life in adults. It's just expressed at different places and on different levels. In not just adults, but in children. Once you start aging as a neonate, about 2 years of age, you've lost most of your FcRn expression in your GI tract. Okay? Then it's predominantly on your endothelial cells and macrophages. What is the job in anybody above the age of 1.5 or 2 of that FcRn receptor? It's now to function by carrying that IgG predominantly across cells to protect it from lysosomal degradation. You're making lots of IgG. Half-life of IgG is about a month, about 28 days, okay? And so the only way to protect that IgG molecule from all of the different enzymes that are being produced, especially if an infection is going on, and thinking about all of the messy eater neutrophils that are maybe an eosinophil that are secreting all of those highly degradated enzymes, is to now just transcytose that IgG across the cell barrier, protect it from the degradation in that environment, and then deliver it to a safer site. Okay? All right, so specialized IgA molecule, so that's the isotype switching that you all talked about in a little more detail yesterday, right? Does it make more sense now after Dr. Frey talked with you, maybe? Okay, so you've got a lot of, I hear a few chuckles. You actually, if you look at the total body, if you look in serum, what's the highest level of your immunoglobulin? It's IgG, right? That's not the highest level in the body. It's actually IgA because of the mucosal surface. You have very little IgA in the serum. But if we were able to scrape off all of the secretions on our respiratory surfaces and look at the level of antibody there, you have massive amounts of IgA. Okay? And it's because of this secretory component, that secretory chain, that when the antibody is made, when that IgA dimer is made, there's a secretory component, a secretory chain that is added that allows it to transcytose across that epithelial barrier, and then it stays locked outside of the epithelium. It can't cross back, so it stays locked in the lumen of the GI tract, in our airways, and is there to function, to bind and neutralize all of those incoming pathogens. Okay. So IgA, secretory IgA is a dimer. There's two IgA molecules that are hooked together by a J, joining chain, all right? So that's one mechanism for getting IgA. The second unique factor is this poly-Ig receptor, and that's uniquely expressed on mucosal epithelial cells, both the GI tract, and as we'll see in a few minutes, in the lung. And that is what allows the transcytosis of this IgA and some IgG from, in the GI tract, from the Peyer's patch, from the serum where it's been made, through that epithelial barrier and into the lumen. And you can see that process occurring in the far right image. Okay? And then just to get an idea about the amount of IgA, you can look here in the bottom and see that the IgA is in yellow here and the IgG is in red. So that's an epithelial barrier. So look at all of those light green, yellow cells versus the relative few red cells. So that will should give you an idea of the relative difference in the concentration of IgG and IgA that is present at those epithelial surfaces. Okay. Interest of time, since I've kind of covered parts of this in a couple other places, I'll let you read through this, but this just basically tells you, and I finally mentioned the Peyer's patch. So here's where you have that highly organized lymphoid structure that in the gut we call Peyer's patch, located right under this M cell. So here are all the M cells in that gold, and there's where you have the transcytosis of the pathogen, delivery to the Peyer's patch, and then the trafficking and the synthesis, and how you trigger that IgA production. All right, and then again, interest of time. Here is the process for making that poly-Ig and the function of the poly-Ig receptor, where you've got that plasma cell secreting the IgA. I'll go over here and talk. Where you have the addition of that J chain in the plasma cell that links those two IgA monomers into a dimer, the addition of that secretory chain that allows passage through the epithelial layer here, and as it passes through that secretory chain, becomes digested to where most of it stays on, but there is the domain that allows passage through the cell is cleaved off. And the lack of that one domain of the secretory chain is what prevents your secreted IgA from then re-entering. It's just kind of a hydrophobic hydrophilic interaction. So now you have that dimeric secretory IgA that is present, permanently present in the gut lumen, in the airways of the cells. Okay? That make a little more sense now that we have a picture to go with it? All right. And remember, there's going to be T cells there, and you've got a mix of both adaptive T cells, so the conventional alpha beta T cells, and as well as the non-conventional gamma delta T cells, and then you have those innate lymphoid cells, the ILCs. All right. Of your intraepithelial lymphocytes, about 10%, a lot of them are those gamma delta T cells. They're predominantly CD8 positive. For your conventional T cells, and most of these are in the lamina propria right under the epithelial barrier. So epithelial barrier is predominantly gamma delta, subepithelial is predominantly conventional, and most of those are CD4 T cells in a memory state. So they may be recruited and then they'll do their job as an effector phase, but for those that hang out there long term, they're predominantly going to be memory cells. But you'll also have, especially in specific disease states, higher levels of Th17 cells and a lot of Treg cells. So there's mechanism number 3 or 4 for how we maintain that suppression and that, we use the word loosely, tolerance to all of those commensal bacteria, because we've got those Treg cells there that are suppressing immune responses. All right, and then all of this happens throughout lifetime. So when you're born, your gut epithelial, your gut immune biome has not yet developed. And so it's a progressive process across the first 2 to 4 years of life, populating the microbiome with all of that bacteria, getting those Peyer's patches to develop, making those lymphoid follicles, and recruiting all of the cells, making all of the IgA, and that sort of gives you an idea. Not necessarily time-wise, since there's not a time factor that's here, but the process that occurs. And it actually starts before you're born. So you've got a prenatal and then a postnatal. Right? Kind of makes sense. Postnatal, once you start eating things, whether it's mom's milk, formula or other things as you age, those foreign products become a trigger for a lot of this developmental process. All right, and then all of the gut microbiome. You're inoculated at birth, but it really takes about 2 to 3 years for that to fully develop. And it changes throughout life, it changes throughout people, due to a number of different factors that you can read there. All right. With normal flora, you get the mucus produced, you get the antimicrobial peptides, all of these cytokines, you get induction and recruitment of more T-reg cells, a lot of IgA secreting B cells to maintain that nice, regulated, calm immune status in the GI tract. When there are changes in the microbiome, when there are changes, whether it's stress, diet, wherever, that can then cause dysregulation. That balance can be shifted, so you've got injury, you can then have altered mucin production, altered production of cytokines. It can switch the cytokine profile. You may have more activated T cells and dendritic cells and macrophages, so now the T-reg cells lose their ability to suppress as well, and so then you can begin to have, number one, defense against pathogens, but if that biome is not readily reestablished, that can become pathogenic. And, anybody remember the commercials with, Jamie Lee Curtis and Activa, whatever, the yogurt she was, it was really rich in lactobacillus, all right? If you take any of the probiotics that are over the counter, a lot of those, if you look at the label, are lactobacillus. So here you can see what that impact is. Again, this is the thinker, so this is not testable at all, but just if you want to see here are some of the elements of the GI microbiome and their specific job in that biome. It's kind of fun. Oops. All right. So part of the dysregulation can be the production of IL-17. If you've got that long-term chronic inflammatory event that's going on, you have lots of IL-17 that can be made, more CD4, Th17 cells produced, bless you, recruited, then you can begin to have autoimmune disease or other inflammatory processes. We know that this process participates in making Helicobacter pylori-induced ulcers. Did you all talk about H. pylori ulcers in micro? No? Okay. So, well, we don't have time to share that story, maybe some other time. But, a lot of ulcers we know are due to a bacterial infection, and that's Helicobacter pylori. One specific GI autoimmune disease is due to a genetic mutation in IL-17. So you have that IL-17. What does IL-17 do? Causes induction of IL-8. What does IL-8 do? Recruit neutrophils. So now you've got lots of those messy eaters that are there just phagocytosing anything they see, because that's the job of a neutrophil, releasing all of those toxic granules which damage the cells, and so then that causes more inflammation, and you get this vicious circle, all initially driven by that misproduction, that dysregulated production of IL-17. Right? Here is one case, as a viral immunologist, I like to think that type 1 T cells, CD8 T cells, those type 1 T cell responses are the most important, right? Here's one case where it's not. In the GI tract, we really, the good default phenotype is a Th2 because you want that antibody produced so that you can secrete lots of IgA, you can secrete lots of IL-4 and 13 to now make those T-reg cells, to enhance the fluid and mucus production, to do some of these other things that we don't normally associate with IL-4 and 13 that can isotype switch to IgE, because how do a lot of parasitic infections occur? Either through the skin or through the GI tract, right? So we want the IgA, we want the IgE, we want those Th2 cells there to help protect the GI tract. All right, and that just goes into a little bit further depth that I'll let you read. There is one, when I was working on this, came across a really interesting paper that said that first developed this lecture 5 years ago, that said, okay, there's this really strong correlation for all of these, the big uptick in food allergies in babies and infants, or not food, but just allergies in general, correlated with the time when all of these natural products came on the market. So instead of using Vaseline or other petroleum-based lotions to keep that baby nice and soft and lovely, we started using coconut oil. We started using all these alternative sources. And so one of the theories behind that change in the disease process is, are we introducing food particles, food antigens, to these babies at a time, number one, through an unnatural route, because it's on the skin, it's not in the gut. And we'll see in the second hour where you've got some processes to protect, but it's not the same processes that normally protect us against food. So is that the dysregulation in the way that the infants are being first introduced to these antigens of food particles because they're being introduced on the skin. So now when the baby eats it, the gut is not tolerized to that particle, and so now it has that food allergy. Interesting thought. All right, so if this clock is right, we're at time. All right, 2 minutes to, I'm not going to run through the slides, but I'm going to say respiratory mucosa, a lot of what we talked about, you see the same processes here. You've got secretory IgA, you've got the poly-IgE receptor, you have mucus-producing cells, like goblet cells in the lung. You have these, it's not a Peyer's patch, but it's the same lymphoid structure that is associated with those cells. The things that are unique to the respiratory tract, you have surfactants, which serve a physiological role, but surfactant A and D, SPA and STD, have a very strong immune role, okay? So they actually can serve as PRRs. If you go back, a month and a half, 2 months, they are listed under some of the elective PRRs because they bind those carbohydrate camps that get to the alveoli of the lung. You have a very special set of macrophages. We don't have a specialized name for them other than alveolar macrophages, but they are phenotypically and functionally very different. The same molecules are also expressed on dendritic cells, but the name alveolar macrophage sort of covers both of those sets. And they are strongly anti-inflammatory, and you can read a little bit about how those work. And again, regulation is important because think about all the stuff we breathe in every day. All the things in the air, not just microbes, especially maybe in further Southwest Virginia in the cold areas, in construction work with maybe asbestos. So you have all these inflammatory products that you can then, here's your alveolar space. Sorry, that's a little vessel in the cell. Here's your alveolar space. So you breathe in all of these particles, that can trigger an inflammatory response. So all of those green areas are lymphoid follicles, kind of like a Peyer's patch, but not exactly, that can develop in the lung under long-term chronic antigenic exposures, right? And that becomes pathologic in the lung because look how much of the alveolar space is being consumed, being eliminated by the development of that follicle, and that then interferes with gas exchange and oxygenation. All right, and then for fun, through with this about the SARS, all of this really pale pink or pale green, that's fluid in the lung, and so that's where you've got the dysregulated immune response, that cytokine storm causing loosening of those epithelial barriers. So you've got dilation of the epithelium as well as vasodilation, and fluid leaks into those spaces. If there's fluid in your alveoli, can you absorb oxygen? No. And then your respiratory microbiome. There is a gut-lung axis. What happens in our GI tract affects the pulmonary system. It affects other systems in the body because of the secretion of cytokines, secretion of other products. And then just a couple slides on the genitourinary. Their genitourinary epithelial system is very different from either the lung or the gut. Both the pulmonary and GI epithelial system are a single cell epithelial layer, or a single cell thick. So you've got that one layer of epithelial cells, that one layer of the undifferentiated cells, and then it's the subepithelial tissue, the connective tissue, right? In the genitourinary system, it looks a lot more like the skin keratinocytes. You've got multiple layers of epithelial cells. Also, you've got very little immune response here. Very little IgA is secreted. The predominant isotype at your genitourinary mucosal surface is IgG. And you have a difference in some of the microbiome. Kind of ignore, these are just, because immunization and tolerance is interesting, and you've got to think about that, but we're not going to make that testable, and then the rest of this is just, again, thinking where you've got dysregulation in your microbiome. If it's a dysregulation in your gut, that can change your response in allergy, in chronic obstructive pulmonary disease, those two highlighted areas, and then that's the end of it. Okay,